Suppose I shine a laser at a very narrow slit. Okay, so I'm drawing the top and bottom of like a sheet of aluminum, like aluminum foil. So this is solid and opaque to light, and I have cut a slit in it. So if I were to look at this from the front, here would be my sheet of aluminum with this little slit in it. So that's viewing it this way. And right now I'm viewing it from the bottom, so I'm looking at the cross section there, as if I've cut it through right here, and I'm looking at it. If I shine laser light on this side, and I get a bunch of plane waves traveling towards it, okay, they're traveling towards it, and they come into this gap right here. The distance between these is one wavelength, and let's say that the width of that gap is A. Right, width of the gap is A. Okay, so the question is, well, what's going to happen? Now, this is a really cool wave phenomenon, not specific to coherent light, but it's got important applications to coherent light. So we could actually see this with water waves, and there's some cool pictures and videos online where some water waves are coming into where there's some barriers that are offshore that have little narrow openings, and the water can come through, and then it does something called, in terms of light, it will diffract. And so what diffraction is, it's a wave phenomenon, and if this light as a wave travels in here, these wave fronts, again this is like a crest, a row of crests and another row of crests for different photons, those rows of crests will actually bend in a circular path coming out of that slit, that hole. The separation between them is still lambda, that's not changed, but they will bend out, and this acts, so this little narrow slit kind of gives the same effect as a speaker. When I have a speaker in a room, the sound goes in all directions. Okay, by shining this laser beam, which initially is going in one direction, I shine that at this slit. This principle called diffraction causes that beam to spread out, and so it goes in all directions. So now this wavefront is traveling in all directions, not just straight forward. Okay. Now, because of that, we can get different types of interference phenomena, because now this light is spreading, and I can maybe cut two holes and have light spread in two ways, so I have two sources of the same light. And we're going to do that in an example next. Before we go there, I want to talk about why we don't see this all the time. Why, if I shine a laser through a doorway, I don't see this. The reason that this happens is when this happens, requires that the gap, this width in the gap, this A, is about the same size as lambda. So again, if the gap is A, then for diffraction to occur, for this to occur, A needs to be similar to, okay, and kind of about the same size as the wavelength. Now, it doesn't have to be exact. It can even be as much as 10 times bigger, but not too much bigger. And if it gets too small, it'll have some issues as well. So it needs to be, kind of about the same size. And generally it's larger. Okay, so when this is the case, we'll be able to see this diffraction. Now, I want to point out, if A is much bigger than the wavelength, so example, if I shine the laser through a doorway or something like that, then nothing happens. This effect is not observed. I shine a light through a doorway or even a centimeter wide gap, and the centimeter wide gap is huge compared to the few hundred nanometer wavelength of light, and so I'm not going to see it at all. It'll just go straight through as if it's just a ray of light. And this condition here is kind of like our governing feature to separate wave nature of light from ray nature of light. Again, when it's similar in size to the wavelength, when the object it's interacting with is similar to the size of the wavelength, then you can start to see the wave nature occur. But if it gets too big, if it's too much bigger than the wavelength light, then you just see the ray nature of light in which it travels in straight lines.